Alright, okay, so let's start. We start chapter 3, new chapter. Okay, so we finish chapter 1 and chapter 2. Okay, so chapter 1 just introduction to thermodynamics, and chapter 2 was regarding working fluid. Okay, and the ideal gas law, etc. The most important part, the pure substance, different phase of substance. Okay, and now we will look at the most important part of this course, which is the first law of thermodynamics. Okay, so we will do just a lecture today. So next week, inshallah, we will look at the examples, tutorial, etc. Okay, so first law of thermodynamics. So again, in some definition introduction, heat, you know by now that heat is a form of energy. So just like work, enthalpy, energy, what else? The internal energy. So heat also is a form of energy which can be transferred from one system to another. Okay, due to the temperature difference. Once we have a temperature difference between a hot medium and a cold medium, so the heat will be transferred from the hot medium to the cold medium. Okay. All right, so next, thermodynamics. So thermodynamics, you know by now, concerned about the amount of heat transfer, amount of the energy, okay, that for a system that undergoes a process from one state to another state, okay. And then heat transfer deal with the determination of the rates of such energy transfer. So what we do in heat transfer is we want to determine the rate of energy, okay, from for example, the vaporization process that we saw last week, from liquid to vapor. Okay, so that in order for the vaporization process to occur, we need to transfer an amount of energy, okay, the latent heat of vaporization last week, or the enthalpy. So that heat, the rate of energy can be also called as the heat transfer, the amount of heat transfer to the medium, to the substance, in order for it to vaporize, for example. Okay, the transfer of energy as heat is always from the higher temperature medium to the lower temperature one. Okay, logic. From the hot body to a cold body. We cannot transfer on the opposite direction, cold to hot. It's always hot to cold. Okay. Heat transfer stops when the two mediums reach the same temperature. When the two medium, the body A and body B, medium A and medium B, reach approximately the same temperature, we say they are in thermal equilibrium. So the heat transfer process will kind of stop. Okay, means that because both of them at the initial point, at the start, they are one hot, one cold, but after they reach the same, approximately same temperature, so they are no more anymore a hot medium or a higher temperature medium or lower temperature medium. Both of them are equalized, we say. Okay, so heat can be transferred in 3 different modes. So we have 3 different modes to transfer heat, which is the first one, conduction, which is usually occur between solid and solid, or solid and fluid. Okay, and the second one, convection. Convection is between fluid and fluid, means gas and gas, liquid and gas, etc. And it also has radiation. Radiation is due to heat source that has medium of light. Okay, sun, and you have or you have light, okay, etc., solar, etc. So that one has radiation heat transfer. Okay, something that has light. Okay, so they has a medium medium of heat radiation to be transferred. Okay, but us here in thermodynamics, I mean in aerospace, usually we will encounter the heat transfer in terms of convection. Okay, here the convection, the second one, because this is more between fluid and fluid, gas and liquid, etc. Okay, so fluid, because we will encounter more aero liquid, okay, fluid, okay. So conduction, it needs at least one solid medium. So this is usually for phase change materials, buildings, wall, okay. It can be conduction process. Okay, almost of heat transfer require the existence of a temperature difference. So once we have a temperature difference, so once the two or more medium has a difference of temperature, higher and lower one. So once we have that, the heat can be easily transferred without any additional appliances, etc. So just a two medium with different temperature, then the heat transfer process will start to occur. Okay. Okay, so for example here, we are normally interested in how long it takes for the hot coffee in a thermos bottle to cool to a certain temperature, which cannot be determined from thermodynamic analysis alone. Okay, so so example here, we have a hot coffee in a flask. Okay, it's like it is insulated or thermally insulated thermos bottle in order for us to keep our hot coffee warm, hot and warm. So we usually use a flask, something like that. Okay, a thermos bottle. So for us to analyze the heat transfer process of the hot coffee to the ambient, okay, thermodynamic analysis alone means just by using the difference of temperature, etc., it's not enough. We need to apply the first law. We need to understand the heat transfer, the internal energy, etc., to the in and out of the body. Okay, for us to understand. Okay, to analyze the heat transfer process. Okay, and then the other one is hot coffee without any insulation material, without any thermally insulated. The hot coffee will easily transfer the heat to the cool environment or the room temperature. Okay, so this is also a types of heat transfer. Okay, so this is the application of heat transfer. You know by now we use heat transfer analysis application in energy production and conversion in steam power plant, gas turbine power plant, gas turbine aircraft propulsion, solar energy conversion, wind turbine, any renewable energy conversion to convert the heat source, for example, from solar to electricity. So we need to understand the energy conversion process, heat transfer process from wind, okay, the wind energy, the wind speed, how to transfer it to electricity. And then what else? We have the ocean energy, geothermal, etc. So those involves heat transfer and of course energy production and conversion. And then we have refrigeration and air conditioning. This one you will learn later in the next few chapters. This is okay. So in heat pump also, okay. This is regarding it applies also the heat transfer process from the hot to cold medium or cold to hot medium. Okay, your refrigerator, your aircon, your what else? Your water heater. Okay, domestic applications, so oven, stove, toaster, again water heater, etc. So those also you apply the heat transfer. Cooling of electronic equipment, okay, in your handphone, your what else? Any cooling equipment that we use, okay. It also relates with heat transfer. Manufacturing, material process, welding, casting, etc. Automobiles, aircraft, and also in nature. Okay, so this again application areas of heat transfer. Okay, so as I mentioned just now, the heat will only be transferred from a hot body to a cold body. Okay, so we to explain further in detail about the heat transfer process, we usually use the theorem of kinetic, the movement of the molecules in the hot body and the cold body is what we call as kinetic theory. So we treat the molecule as tiny balls, small molecules, like small balls in motion, thus possess kinetic energy. So we assume that the molecules inside the body, our liquid, our gas, our solid, etc., contain molecules. So these molecules are always in motion. So they possess kinetic energy. So that's why during the heat transfer process, the kinetic energy will be transferred. Okay. And the rest is historical background. Okay. So this is the famous scientist where we got his name from, Joule. So that's why we use the units for energy in Joule. Okay, now the most important part, moving boundary work. Okay, so now let's understand about, we know the energy, okay, heat transfer, etc. So other types of energy other than heat is also work. Work is also energy. Okay, heat is energy, work is also energy. So that's why we want to produce in a gas turbine, we convert the heat to work and power. Okay, so moving boundary work. Working system, gas confined to a cylinder fitted with movable piston in thermal contact with a heat reservoir to exchange heat, which is Q. Okay, Q is heat. Okay, so example, we have a piston. We have a piston. Okay, because we involved with piston engine, for example. So the system, our system is a cylinder. So we have a piston usually on top. Okay, we can move the piston. Okay, so the piston will do the work. Okay, the work that we are talking about, we compress or it will go downside or upward. Okay, initial state of the system. Okay, at the initial, we assume that we have a pressure, IV, velocity, volume, and temperature. Initial state. Change to final state of the system. PF, final pressure, final volume, and final temperature. Do you remember these three parameters, physical parameters, that are most important for us in thermodynamics? Through absorption, positive Q, or release, negative Q. Okay, so when we assume that when we how to say, when we compress, okay, compress the piston, okay, so it is in absorption, it's called absorption also. It will be a positive Q, means the value, the amount of heat will be in a positive value. And release, okay, when we take out the piston upward, okay, it will be somewhat released. The gas, the fluid inside the cylinder is released. It will be, the value will be negative Q. Okay, it is due to the direction. Okay, direction of the work. Okay, so if the work goes down, okay, so it will be in this direction, negative. So upward, positive. Okay, so it is due to that. So when we calculate the amount of heat Q, if we have the value positive, so means that it is absorbed. If it's negative, then it's released. The heat is released by the system gas. Also, work can be done in raising the piston. So work also can be positive or negative. So actually it's opposite. If you have positive heat, then negative W. Okay, so we see later on. Okay, so this is the term, the equation. Okay, the expression for work. Okay, the boundary, for boundary work, we usually write it down as W, work, and the integral of pressure and volume. So actually, we can describe the process in terms of pressure versus volume. So we do the integral, means we calculate the area of the pressure versus volume. So we get the work, the boundary work done. Okay, because when we do the piston, when we release or compress the piston, it's like pressure work. We do a pressure, right? We compress or we expand the piston. So it is like a pressure work. Okay, so that's why pressure is in here. When we want to calculate the work done, it involves pressure, because we put pressure or we release it, expand it, okay, the piston. And it involves with it depends on the volume of our cylinder, our piston. So that's why the pressure and volume is here. Okay, understand? So that's why the moving boundary work relates with the pressure and volume, of course. Okay, so here we can see maybe clearer view with the graphic here, surface. Okay, so it's like we are calculating the surface area under the curve of the PV diagram. So DW, okay, work is also in static. You learn in static, work is force times displacement. Okay, but here, thermodynamic or in fluid, the force here is the pressure force. Okay, so force here is PA, pressure times the area. Okay, so it's still force like the static. Okay, work it seems it is the same as in static. Work is force times displacement, but here the force is the pressure work. Okay, so pressure times area, and the ds is displacement. Okay, the change in the displacement. So ADS is volume. Okay, the area times the displacement is volume. So we have, that's why we have dW equals to PdV, and then we do the integral. So that's why we have this. That's how we have this relation. Okay, so it comes from the definition of work in static. Also you learn, I think. Okay, force times displacement. Okay, so work done represented by the area under the curve on PV diagram. Okay, so it is like the path taken. Okay, area depends upon the path taken, initial and final. So it depends on the initial and final state. So if, for example, even though the volume is between this and this here, but the final maybe here, so the total moving boundary work, if you look at the area, it will be different. So it depends on the initial and final state. It doesn't depends on the difference of volume, etc. Okay, so so if you see, okay, this one is the first general one. We just do the integration, so the work will be positive value. Okay, but for B, this one, this example, from I, the initial state, to A here, process volume increase at constant pressure. So I to A, the pressure is constant, and then A to F, the volume is constant. Okay, so here it only depends on the volume. Here it depends on the pressure. So the total boundary work is like a square area. Okay, and then for this one C, okay, for this one C, okay, so you can also see if the path taken from I to F is different, so the moving boundary work also will be different. Okay, even though the initial and final state are at the same point. Okay, look at B and C here. Initial and final state are at the same point, but the path taken are different. The process along the way are different. Okay, from I to A and from I to this point, maybe B. Okay, so the moving boundary work will also result differently in different value. So it depends on initial and final state, and it also depends on the path taken of the process. Means the process, how are we going to how the process evolves from initial to final state. Okay, again, moving boundary work. So again, you have, okay, usually it is written as WB, boundary work. Okay, so this is the integration, the same just now. A gas does a differential amount of work as it forces the piston to move by differential amount of ds. So if we do this, if you write this relation, it means that a small movement, displacement here ds will result in a small boundary work. Okay, and then so here the boundary work, if it's positive, positive negative, means the positive value is expansion process. Okay, we release the piston, so work is in this direction, y direction, positive. So expansion, we release the piston, so that is expansion process. So if boundary work is positive, so it is expansion. If the boundary work is negative in this direction, downward, so the process is compression. Okay, it's just easy as that. Positive, this direction, expansion, negative, compression, downward. Okay, so quasi-equilibrium process, a process during which the system remains nearly in equilibrium at all times. Okay, why this is important, why we need to assume a quasi-equilibrium process means that because for actually if we want to apply for example our first law of thermodynamics later, the energy conservation, actually it's like we assume that the mass, the temperature, the pressure, etc., from the initial to the final state throughout the process exactly. I mean, it doesn't change. I mean, between the process, okay, how to explain? Okay, when we say that the process is quasi-equilibrium, okay, why we need to assume this? Because when we want to apply the first law of thermodynamics, for example, the expression of energy, we only know the value, usually we only need the value of initial and final. Okay, initial and final of our process from 1 to 2. And when we apply the energy equation, the first law, since you only know the initial and final point values, location, it's like we are assuming the movement, the mass, the temperature, pressure during the process. For example, from initial to final, we are like this here. The journey is like this process, but so along the way from the initial to the final to the final point, in reality, usually our piston, our system change with pressure and temperature. Okay, but we are assuming that the process is quasi-equilibrium, means the system reach a equilibrium state at each small point also, so that we do not need to define the pressure, the temperature, the mass along the journey. We only need to know the initial and final. Otherwise, if we don't assume, if we don't make hypothesis that our process is quasi-equilibrium or nearly equilibrium, equilibrium means nearly equilibrium at each state, we need to know at each point what is the pressure, what is the temperature, what is the pressure at point A, B, C, D, E, until it reach the final state. Okay, to in reality, because along the process from initial to final, obviously, if you look into detail, our system will change the physical value, the mass, etc. along the process. So actually, when we apply our law, the equation, etc., we are only calculating it in approximately, roughly, not actually the exact amount. So when we assume that our process is quasi-equilibrium, we don't need to know the value, the physical properties, pressure, temperature, mass, etc. at each point along the journey. We only need to know the initial and final, and we assume that they don't change. They only change initial and final. They don't change along all the other properties doesn't change along the way, along the journey of the process. Understand? But in reality, if you do research for your higher degree, master, PhD, or even for your FYP later in final year, if you involved with this, actually you need to be more precise. So you cannot simply assume it is quasi-equilibrium. You need to know at each point. That's why you need to do a modeling. You need to program the system and do some loop calculation, modeling, numerical methods. Okay, so it's become more complicated. Okay, so here we assume it is quasi-equilibrium for thermodynamics. Okay, for your project, etc. later in your final year, it will be different. Okay, So the work associated with a moving boundary work is called boundary work. Moving boundary is called boundary work. Okay, so okay. Okay, so the area under the process curve on a PV diagram represents the boundary work. So here is we already see just now. So we do the integration. It's like we are calculating the area. What else? The boundary work done during a process depends on the path. Okay, this is already done. The net work done during a cycle is the difference between the work done by the system and the work done on the system. The net work done during the cycle is okay. It's like the total the network total cycle, the total cycle work is different, the network. So you usually you do the difference of work output minus the work input. Okay, so usually the work output is from the expansion turbine process and the work input is from the compression. Okay, polytropic isothermal and isobaric process. Okay, at least you understand this. This just the definition. Okay, polytropic no need. Isothermal means a constant. The process occur in a constant temperature. Okay, so what will happen to your moving boundary work just now? Okay, the calculation of your moving boundary work. If you have a isothermal process, constant temperature process, your boundary work will become after integration. This is we are using the ideal gas law, PVRT, last week. So if the process is temperature is constant, so your boundary work will be like this: PV ln ln V2 over V1. Okay, by using you replace P with the ideal gas equation MRT over V. Last week we have learned MRT over V is the ideal gas equation. So you just replace P with the ideal gas equation and then you do the integration. So for isothermal process, since the temperature are the same, T2 and T1, so you can simplify that. So you only have PV ln V2 V1. If we have isobaric process, means the pressure is constant. So your boundary work, you can, the pressure doesn't change, it is constant. So you just integrate dV. So your boundary work will be P, the constant pressure value, V2 minus V1. Okay, so that's how your boundary work change when the process is isothermal or isobaric process. So question here, what is the boundary work for a constant volume process? We know that for just now for constant temperature, isothermal, the term will become like this. For isobaric, constant pressure, the term will become like this. If constant volume, or we call it isocore, what will happen to the boundary work? Anyone know? Looking at the term, the equation, what will be the boundary work for constant volume? Just easy questions. You look at the equation, what will be the boundary work? Nur Absharina, let's do that. Nur Absharina, what do you think? Okay. No, you are not here, Absharina. Okay, I call another one. So consider Sharina not here. Tang Jiajun.
Yes, doctor.
Okay, what do you think will happen to the boundary work, WB, if you have a constant volume process? Just look at the equation. No need calculation. What will happen, you think?
Increase,
The integration. Sorry?
increase or
You increase? Okay, Praveen type in the message 0. No boundary work. Okay, it's okay. Thank you, Jiajun, and thank you also Praveen. Okay, so the boundary work 0. Okay, just look at the here in the expression, the volume doesn't change. So dV 0. Okay, the difference in volume 0, so boundary work 0. Okay. All right. Next, okay, workforce time displacement. This is in static. Okay. Is that when you want to calculate work, you do the F cos theta, etc. This one more for mechanical. And then unit of work, okay, again, unit of work in SI units, we use joule or kilogram meter square per second square. Okay, more about work. Okay, the work done by a force. Okay, this interesting. Okay, just now we mentioned that boundary work for volume 0. No, constant volume. The boundary work will be 0, right? So the same thing in for solid mechanic. The work done by a force is 0 when the force is perpendicular to the displacement. Okay, when the force so when the force is 90 degree, okay, to the movement of the fluid or the system, so it is like a constant volume, doesn't change. Okay, so force times the displacement 90 degree, the same direction. So you have cosinus 90 degrees, so the work will be 0. So the same thing as the constant volume example just now for fluid. Okay, so static also, force and displacement same direction, so both will be 0. Okay, same direction, positive, so this is also the same. So for example here, okay, the example of the work 0 for in static. Okay, if the force is vertical and at the same time the movement of the system of the mass also in the same direction, so no boundary work can be done. EO is done. Okay. What can be positive or negative? Okay. This is power. Okay. And then power is simply work, a ratio of work to times in seconds. Okay, so it will be in watts. Okay, so that's why for our gas turbine, either we calculate it in terms of joule energy, or we can also calculate it in terms of power, watt. Okay, so we just divide by time, the period of time of our process, so we know the power. Okay, so kinetic energy, KE 1/2 mv square, the movement of the system. And then you have potential energy. So all of this will be included in the first law thermodynamic, conservation of energy. Remember, energy cannot be created nor destroyed. So it can only be transformed from one form of energy to another form of energy. So for example, you transform the heat to kinetic energy, you transform the work to potential energy, example. So it will be, the total energy will be always balanced, okay, conserved. So you have kinetic energy, potential energy, gravitational potential energy, okay, MGH, etc. This is more for static, so that's why I just go a bit fast. Potential energy in a spring, so you have the Hooke law, okay. Transferring energy by a rate of force. Okay, so how are we going to transfer the energy from one point to another point? Okay, one method that we can use is by applying a force work. So force and the displacement, so you produce work. Heat, okay, again heat, transformation from the hot body to a cold body, heat. And then we also have for radiation, heat transfer through radiation. Just now we have mechanical waves, sound, water, seismic, etc. Okay, this one not we are not going to use this regularly. Radiation, electrical transmission. These are all example of energy transfer. Okay. So again, conservation of energy, we can neither create nor destroy energy. Another way of saying energy is conserved. Okay, if the total energy of the system does not remain constant, the energy must have crossed the boundary by some mechanism. Applies to areas other than physics also. Okay, so these to ensure that the energy, this sentence, this theorem are valid. That's why we need to derive this first law of thermodynamics. Okay, energy and mass. Okay, specific heat. Okay, so again, specific heat is the amount of energy that we give, okay, or we reject, okay, per kilogram of mass and per Kelvin temperature. Okay, so a substance that will enable us to compare the energy storage capability of various substances. So it depends on the different substance. For air, it's different specific heat. For carbon dioxide, different specific heat. For solid, different. For different types of solid, the specific heat will vary, etc. So it depends on the substance, the material. Okay, so the energy required to raise the temperature. So specific heat is energy. It's just that it is regarded as per kilogram per degree. Okay. So specific heat, it has two types. One is constant volume specific heat. It's written usually as CV. Another one is constant pressure specific heat. It's written as CP later. Okay, I show CV first. Okay, constant volume process. For a constant volume process, so the boundary work is zero and the specific heat is identified by, okay, remember just now for constant volume process, the boundary work is zero. So from the first law of thermodynamics for closed system, so the first law of thermodynamics will only have this term. Okay, so actually is a long equation. You have heat, you have work, you have internal energy and the fluid energy, which is enthalpy, and you have kinetic energy and potential energy. So for this application in our thermodynamics, so we assume we are applying this to a control volume like a nozzle, compressor, turbine, etc. So there's no kinetic energy and there's no potential energy. Okay, so we're only left with heat, work, internal and fluid energy, the PV, enthalpy. Both of these are enthalpy. Internal and the fluid energy, both of these are plus each other, is called as enthalpy. But here we don't have, in this example, usually we don't have the boundary, since the boundary work is zero. So this is like the boundary work also. So this is zero. So we left with internal energy, work, and heat transfer. So Q, W, and du. The first law thermodynamics only simplify as this. So if the boundary work is zero, so we have heat transfer equals to internal energy. Delta Q equals to du, and du also, the internal energy. The definition of internal energy is the change of temperature with the specific heat at constant volume process. This is definition of du. So that's why when delta Q equals to du, the difference of internal energy, so we have delta Q, CV, delta T. Okay, so this is what CV, specific volume, specific heat for constant volume, du over dt, internal energy. Okay, so and then for constant pressure process, okay, we use CP. Just now CV ni CP. Okay, so again the first law of thermodynamics. So this one, our work is the fluid work, the fluid energy. So we have delta W will become the plus PdV from the enthalpy. So this is enthalpy, U plus PV, H equals to H, enthalpy. So you have delta Q equals to Cp dt because dH is Cp dt. Cp dt is a difference in temperature, not time. Okay, so Cp is the ratio or the differential form of dH over dt. This is the definition. Okay, so us for gas turbine, we use more CP. CV usually is for liquid or solid. But for gas, usually we just apply this one CP. Okay, so ideal gas. Okay, ideal gas. So what happened to the ideal gas? So we have the ideal gas equation from last week, PVRT. Okay, so replacing this PVRT in the energy first law equation just now, H equals to U plus PV. So PV is RT, so you have U plus RT. So you can see that the enthalpy depends on the temperature. By doing the integration, so you have CV, the same expression, du over dt. And again, okay, so again, the same for delta H also. Delta H equals to Cp delta T. Okay. And this one, okay. I will use this one, okay. So finally, this one, for ideal gas, okay, this is what we are going to apply a lot for thermodynamics and gas turbine propulsion. So we use this one, dH equals to CPDT, all the derivation just now, this mathematical form, okay, this is how we derive, but the one that we are going to apply is just this, okay, page 45. Okay, so H equals to U plus PV, so PV is RT from the ideal gas equation. So you replace the H with CPDT, U with CBDT, etc., etc. So we got this this expression, alright? Simplify the dt. So we have Cp equals to Cv plus R. Okay, R is the gas constant. Gas constant, specific gas constant. Okay, so the value for R per kilogram per Kelvin, again 0.287 kilojoule per kilogram per Kelvin for air. So again here, specific heat ratio, K or gamma is Cp over Cv. So this has no unit. Okay, it's just a value which is for air is 1.4, or for usually air that we use in gas turbine, we use the value 1.33. For ideal gas is 1.4, sorry. Ideal gas is 1.4. For air that we use in propulsion, usually it will be 1.33. Okay, otherwise it's just 0.1 difference, so it doesn't matter. And Cp is Cv plus R, and we can also write by using these two terms, two equation, we can also rewrite Cp and Cv in terms of gamma R. So means that we are assuming that Cp and Cv are constant, which is in actual reality, this specific heat usually varies with temperature. But here we are just assumed to simplify our calculation. We assume it is constant. So once we know the gamma and we know the R, for example, for ideal gas, gamma we take 1.4 and R we use 287 joule per kilogram per Kelvin. So once we know that, we can calculate the Cp, which become 1005 joule per kilogram per Kelvin for ideal gas. Okay. Okay, I think that's all for today, introduction to the first law. So what the most important part for you guys is to understand, I think the few last slides, okay? Just the few last slides, the first few slides just now, starting to understand the concept. Okay, the moving boundary work. Okay, the moving boundary work also important to understand about the moving boundary work. We will apply that, and this one. Okay, this one for IUS, our fluid. We will apply the first law thermodynamics. So we are using this enthalpy, internal energy, Cp, dt, etc. Okay. So yeah, any questions regarding this chapter? So we will look at the example next week, inshallah, after your holiday. But if you want, you can start do the example. So we have exercise 1 to exercise 5. So basically, first law and even second law, the lecture or the theory is quite short. But the exercise is more important. So when you do the exercise, you do the tutorial, you look at the example, you understand the different process. Okay, so again, what we learned last week also we need to redo again and again, do a lot of exercise more regarding the phase change, liquid, vapor, superheated vapor, etc. So that one also important. So we combine all that, the different phase change and the first law together. So we have to get both of these part have to be done. You need to do a lot of exercise because the theory is very short. You just apply the first law thermodynamics. That's all. But you may encounter different process, different energy transfer. So it can be sometimes it can be difficult a bit. So you need to try on your own. Okay. Any questions?
Doktor, saya nak tanya untuk yang slide 12 tu,
Ni dah.
yang PV ln V2 over V1 tu adalah proses isothermal ke?
Kat sini tak ada nombor 12. This one
Yup, betul.
Which one? Okay, which equation?
PV ln V2 over V1.
This one. Your question is?
Is it isothermal process?
Yes, isothermal process. Actually, okay, so this is the general equation, right? Boundary work integral PDV. So this P you replace with the ideal gas. Ideal gas kan PV equals to MRT, right? Okay, so you replace this P jadi MRT over V. Okay, that's why V ni patutnya kat bawah lah. Dia -1 ni bawah lah kan. Okay. So MRT over V, that MRT, M mass constant, R constant, T here isothermal, so T constant. So that's why this MRT, they just write it as C constant. So C over V ln lah, integral. Okay. Understand tak?
Okay, doktor, dapat doktor.
Okay. So because MRT tu constant, so they just write it C and then just do the integral ln and then rewrite again PV from the apa tu MRT kan equals PV, so tulis balik lah PV tu. Okay, any more questions? Okay, nothing. Okay, try to digest, try to re-look back at this lecture. I think I've uploaded in Putra Blast. I have, right? Saya dah upload kan rasanya. Okay. Kalau tak boleh cakap lah kalau tak. Saya rasa macam dah. Okay.
Dah doktor.
Dah okay, boleh tengok Okay, if nothing more, we stop here. So I'll see you guys next week.